Let's calculate the distance using the Hubble-Lemaître law to a nearby galaxy, and the one we're going to look at this time is M32, Messier object number 32, or the New Galactic Catalog number 221. And here is the image of the galaxy as observed by the two-mass space telescope. Now we're given that the radial velocity, or the speed of the object that's either moving towards us or away from us, is given a value of minus 200 kilometers per second. So it's negative 200 kilometers per second. We want to find the z value, and we also want to find the distance in megaparsecs. So let's take a look at the equations that were given. Z is the redshift parameter, and that is equal to the radial velocity divided by the speed of light. And we're going to use, in this case, the speed of light is 3.00 times 10 to the 5th kilometers per second. When we take a look at the radial velocity in terms of the Hubble-Lemaître law, we have the radial velocity is equal to the Hubble constant times the distance to the galaxy, where the Hubble constant is 68 kilometers per second per megaparsec in this example. So let's go ahead and solve. First thing we want to solve for is z. So we're going to choose just black color. So let's start with A. And we want to solve for z. Z is equal to the radial velocity divided by the speed of light. We're given the radial velocity. The radial velocity is negative 200 kilometers per second, and we want to substitute that in for v sub r. Now the value is negative. Since the value is negative, it's telling us that this particular galaxy is moving towards us. By design, negative in this case is towards us. The value for c that we're going to use is 3.00 times 10 to the 5th kilometers per second, and we're going to substitute it in there. And I'm just going to shorten it to 3 times 10 to the 5th. Since we have like units of kilometers per second, both in the numerator and denominator, we want to go ahead and cancel letters and numbers, anything that we can. We can cancel kilometers per second easily, leaving a unitless number on the right-hand side. Now all we need to do is divide 200 by 3 times 10 to the 5th. So we go to our calculator that we look up on Google, and we divide by 3e5, and we get a value of 0.000.666. So we have 200 kilometers per second divided by 3e5 kilometers per second, and we're given a value that we calculate out of a very low z number of 0.000, and the value is 66, and we'll round one of these sixes up to a 7. So 667. And it's unitless, so I'm just going to go ahead and put a z here. And then I went and made the absolute value. I dropped the negative, so I'll go ahead and put the absolute value sign on the left-hand side, indicating that I'm just looking at just the number, not the direction. So let's take a look at this number. Since z is less than 1, we know that the galaxy is nearby. So we can just write it down that the galaxy is nearby. So that's our clue to us, because you're looking at the value for z. So we're going to look at a convention of anything less than 1 is near, anything greater than 1 is far. All right, let's take a look at B. B says we want to find the distance in megaparsecs. We have our equation of the radial velocity is equal to the Hubble constant times d. We want to solve for d, but we need to plug in our values. Our radial velocity is minus 200 kilometers per second. So we're going to put that in on the left-hand side. And then we need to put h naught and d on the right-hand side. So h naught, we're given a value of 68 kilometers per second, and I'm just going to make a small kilometers per second on the top because I want to put them both in the numerator. And then I'm going to put a big division sign, and we want to put per megaparsec, which that per is that big division sign, and we want to put megaparsec in the denominator. And then we want to multiply this by d distance. We want to solve for distance, but before we do that, we want to divide like quantities, either letters or numbers. We can easily get rid of kilometers per second on both sides of the equation. And now what we want to do is we want to multiply on both sides of the equation something to get rid of everything on the right-hand side, so we just have left with just d. And so we need to figure that out. So I'll put my division sign in here. We don't like megaparsec in the bottom, so we're just going to put megaparsec letters in the top. And if you feel comfortable putting the 1 there, go ahead and put a 1. And then we have 68 in the numerator. We don't like it, so we're going to put 68 in the denominator. And then we're going to copy everything over to the other side, so it's the same, and 1 megaparsec on the top. Now we can go ahead and cancel letters and numbers. So we have 68 is the number on the numerator on the right-hand side, divided by 68, the denominator on the right-hand side. Megaparsecs in the numerator on the right-hand side, divided by megaparsec on the denominator, so we can cancel those. Left-hand side, we really don't have anything easy to cancel, so now let's just carry everything down and multiply. So we're going to carry our equal sign down. On the right-hand side, the only thing we're left with is d. We do have a 1 here, but 1 times d is just d. On the left-hand side, we have a 1 times a minus 200 divided by a 68. So let's go to our calculator. We have a 1, multiply it by a minus 200 equals, and we want to divide it by a 68 equals. So we get a value of minus 2.94, and 1 is less than 5, so we can drop it off. So we're just going to keep the minus 2.94. So we've got a minus 2.94. And we have units. Megaparsec is what's carried over. Now a value of negative 2.94 megaparsecs doesn't really make any sense. So I'm going to make it a positive and put the absolute value here. And then put it in a box. Our distance is 2.94 megaparsecs. Now let's take a look at this. We're looking at a nearby galaxy, NGC 221 or M32. We notice that our z value is less than 1 by a lot. So this is a nearby galaxy. So this technique to find distance that we're using, the Hubble-Lemaitre law, is not the best law to find the distance to this galaxy. This Hubble-Lemaitre law is used to find distances to faraway galaxies, galaxies that has z's greater than 1. We calculated a distance of 2.94 megaparsecs. In reality, this galaxy is only located at about 3/4 of a megaparsec. We're off by, what, 4 times using this particular method for finding the distance to a galaxy. You can use the Hubble-Lemaitre law, but it's best to use it for a faraway galaxy. And you determine whether it's far away or nearby by determining its z value. Let's take a look at where M32 is located, just so you can get an idea. This is M31, the Andromeda galaxy, and M32 is right there. That's your elliptical galaxy that is a satellite galaxy of M31. And that's how you find distances and z values using the Hubble-Lemaitre law to nearby galaxies.